All right, we are on to maps. So here is the documentation for the map and the link to it. As we talked about last week, the map abstraction is a key value pair abstraction, and it is a way to connect two pieces of data together. And so typical operations that occur in the map API include having key and value associated with the constructor of the map, the declaration of the map. And then in order to insert key value pairs into a map, it's actually abstracted to be the same as a vector or an array. So the square brackets, the square bracket is how you insert a key, and then the right-hand side of the equals sign is where you insert the value. So it's really clean syntax. A lot of other APIs for maps have different syntax than this, where they actually push in the key value pair, but the C++ API uses this syntax where you use the square bracket to put in the key. So that's how insertion works. And then lookup is actually the same, which makes it a little bit confusing. So if you need to look up to see if a value is in the map, you just access the map via its key in the index. And so we'll talk more about some of the operations, but that's kind of a little bit of a quick tour of the way the API works. And this is our final solution to this UIN NetID code that we've been writing for all these different abstractions. And you'll really see the power of maps because maps do this, problem the best. It's not to say that maps are the best, but maps, it'll show maps strengths and perhaps not give stacks, queues, and sets enough credit. But they all have their applications of when you would use them. And so this example that I'm using is definitely best suited for a map. So here's the constructor for the map. Again, key value pair is indicated here instead of just the container that has the one value. How's a map implemented? So maps are implemented the same way as a set with a binary search tree under the hood. In fact, they're really similar to sets. Sets and maps are almost the same thing. It's just that a map carries with the binary search tree more than one thing, where the set only carries the value itself. The map is able to carry also other things like, you're mapping the key to the value, so the value comes with the binary search tree as well. So that's a little bit about the implementation. And so it has the same features where you can walk through the key values or the keys in sorted order because they're part of a binary search tree. So let's write the same function with a map. Again, we're going to fill it, print it, and search it. And this one is particularly good. So let's look at it. So let's start by, I'm going to just show you a little demo and then I'll walk through it again on the slides. All right, so here's that code again. The code has all four of the implementations. And so for the maps, let's just run it. So I'm going to first start with a bad implementation of search. So let me show you these functions quickly. So filling the map is, just using this insertion operator that I already showed you. The rest of the code is the same as the other abstractions. Printing is also the same. You just use the for each loop. The only difference is because there's key value pairs, it's actually using something called a pair in C++, and that syntax is that you access the element from the map and then use first and second. So first will get you the key and second will get you the value. And then we're going to do this search. And this is called bad, and you'll see why. But I told you that lookup is going to work the same as insert, basically, right? So if I want to find a net ID given a UIN, I just use the UIN as the index to the map and it will give back its value, which is its net ID. If it doesn't find anything, then it will return an empty string or whatever the null equivalent is of the type. And so then we know it's not found, otherwise we know it found it. So when we run this, first it loads in the map and then it prints it out, and so we have this nice key value pair between UINs and net IDs. So this one's going to be really easy to read compared to the others, because if I look up any of the UINs, I'm going to get out the net ID. And unlike the other ones that sometimes couldn't even tie these two together, this one ties it really well. So now let me look up a UIN that doesn't exist. So it's not found. Look up another one, just randomly typing. What you're going to see is those random numbers that I typed in during my lookup get inserted into the map. And that's the unfortunate part about that lookup operator that I showed you, is that its default is if it does not find it, it adds it to the map with an empty string. So that is not how you do lookup. You can't use this for lookup because obviously if you're looking something up, there has to be a lot of cases where it's not there, so you don't want to do that. So the good version of search is to use some of the other member functions, and one option is count, which works just like set. So you just call count. If it returns 1, then you know it's there, and then you can extract it because you already know it's there, so you're not ruining anything. There's also a function called find that you can also use, and it works the same. I mean, it's different, but it can also be used to properly do lookup. So now let's change this to the better version of search that does count instead of just straight looking it up into the map. Do I have another terminal open somewhere? Or is this really just this slow? Okay, so check to make sure lookup still works. That's good. Random, random, exit, and you can see that now the map does not have those things in there. So that's how a map works. There's some kind of finicky things about it, but the basic idea is that it's filled with this insertion, operator that works just like vectors. And because it's a binary search tree, this is log n when you do any insertion, because all it has to do is walk through the binary search tree, and that takes log n operations. To access, you can use you can access in with the square bracket operator, or you can use the for each loop, which will walk through all of them. One thing I wanted to point out is that just like with the set, it's going to be walking through it in sorted order. And so the arrow should be pointing here, but it's going through in sorted orders of the keys. So our UINs are our keys, and you can see those are in increasing order. What's the big O of access? It's also log n. But remember, no direct access with maps, but if you need to access one of the elements via its key, it's log n. Search is the same as access, right? It's the same thing for a map, and so it is also log n. And this is the example of search being used in this bad way where you're calling this first because it will add to the vector. So here's an explanation in code or in a slide of what I just showed you in the code, which is basically that it's going to add things to the map while you looked it up. And so the good version of the code that I showed you is to use count here so that you can determine first if it's in there. That's still log n, right? Everything's log n, so count also is log n, and all count does is does a lookup into the binary search tree. So maps have log n everything. They have for each loops that go through their keys in sorted order. Does a map have an at function? Why did I put that? Map, C++. If it did, I did not know it did. C at. Oh, it does. So it does have the at function. I've never used that, but it must work very similar to the square bracket. But just remember that they do automatically add keys to the map if they're not found, so they shouldn't be used for search alone. Maps have very fast lookup, and size is the same as we've talked about with every other container. But just like sets, there are two types of map containers. There's the map container we've been talking about and the unordered map. The unordered map is the same as the set. It has a hash table behind it, and so there's a couple things that are different. It's faster. There is also no order. It's not sorted in any particular order, but it's faster. And so again, we don't want you using these yet in your code. We need to talk about them a little bit more, so just stick with maps for now, but just know that they exist. So you have all this O1 access, insert, search, and remove, which is amazing, but they no longer maintain an order. So how is that possible? They have a hash table instead of a binary search tree under the hood. And hash tables are amazing. They're just a little bit less general, and so sometimes they have to be customized. So just like with the set, you might need to work a little bit on a hash function to make it work for your data. So it's not quite as straightforward to use, but really, really cool, and we will be talking about it in a later lesson, all about hash tables and hash functions. They're really, really fun to work with.